In severe weather scenarios, we often hear meteorologists talking about CAPE and CIN. While there might be a few people that are really talking about donning their best storm-chasing attire, generally we're talking about convective available potential energy and convective inhibition. These have been some long-requested features in MetPy, and this week we're going to show you how to use them. Hello, I'm John Lehman. I'm a software engineer at Unidata, and this week I want to show you how to use the CAPE and CIN calculations in MetPy. These are some of the most requested things for a long time, and as it turns out, there are a lot of different ways to calculate them, and it's actually pretty hard to get a reliable calculation that works with all of the weird things that happen in real-world data. And speaking of real-world data, that is the first thing that we need to do, is get some data. We've covered this before in previous MetPy Mondays, so I am going to grab some data from a case that we've seen, April 14th, 2012 in Oklahoma. Okay, so what I did is I pulled that data in using Siphon, and went ahead and pulled out and attached the proper units to pressure, temperature, dew point, and heights, because I'm going to show you a little trick with heights towards the end of the video. So we know that this is going to live in the calculations module, so we're going to go ahead and import metpy.calc as mpcalc. And then we're going to actually be able to calculate in one line CAPE, but we need to know what CAPE and CIN you're talking about. As it turns out, there are a lot of different ones. There's surface-based, there's most unstable, there's mix layer, which can be over any layer that you specify. And we're working on implementing different versions of these in hopefully a robust and way that you can specify different parameters and different assumptions to make, like what kind of adiabats to use, or is it reversible? But for now, we'll stick with simple surface-based and most unstable CAPE. Let's start with surface-based. This is the most straightforward one. We're taking a surface parcel, computing the parcel path, effectively looking at the area between that parcel path and the measured environmental temperature with some constants thrown in. So mpcalc dot, I'm going to start typing surface, and if I hit tab, it goes ahead and tab completes surface-based CAPE CIN. If we look at the doc string, remember shift tab to get a preview of that. It wants pressure, temperature, and dew point profiles, which we can provide. And when we run that cell, we get two return values. The first is CAPE, so a little over 1.1 kilojoules per kilogram, and then about minus 8.2 joules per kilogram of CIN there. Now we can do the exact same call, except replace surface-based with most unstable. What this does is find the most unstable parcel, and then uses that as the starting point for the parcel path. So if we type most and press tab, we can see we could actually calculate what that most unstable parcel is. But in this case, we want most unstable CAPE CIN. It'll take care of that other call for us. Pressure, temperature, dew point. And we see that we get a higher number because this is the most unstable, and there is no CIN in this particular sounding. So we're looking at about 1.4 kilojoules per kilogram there. Now there is a very generic version of this CAPE CIN calculation that's actually what these two functions are calling under the hood. It is just mpcalc dot CAPE CIN. You see that this takes pressure, temperature, dew point, what we're used to, but it also takes a parcel profile. So it does not calculate a parcel profile for you. You can give it any parcel profile you like, as long as you provide a temperature at each pressure level that's in the pressure array. So here you could specify whatever crazy thing you wanted. You could change the surface temperature up or down. You could do a sweep to see what happens if that changes. You could make little isothermal layers, whatever you wanted to do. You could do that, and we would calculate CAPE CIN given that profile. One of the other things that you might commonly want to do is calculate what's the CAPE from the surface to 3 kilometers. That's something that we might want to know. And we can actually just trim this data down to surface to 3 kilometers and then call these calculation functions like we have been. And there's a convenience function called getLayer. Now, getLayer itself could be a subject of a whole MetPy Monday, and probably will be. It's a really complicated and really versatile function. We're just going to scratch the surface of it today. The first thing is we know that we're going to be specifying a height, and we're going to want to use units for that. So we need to import our units registry. So from metpy.units, import units. And then we can go ahead and look at this getLayer function. So mpcalc getLayer. If we tab complete, we see that it takes pressure and then arguments and keyword arguments. So here's where we want to look at the whole doc string a little bit more. So we take pressure, an arbitrary number of variables that we want to get this layer over. Heights, if we want to give it heights, otherwise it'll use a standard atmosphere. A bottom, it will assume the surface if we don't give it anything. The depth from that, and then whether we want to interpolate, and that defaults to true. So that means if there is not a data point at, say, 3 kilometers here, then we're going to interpolate the 2 closest data points and go ahead and get you exactly to that bound that you specified. Okay, so now I think we're ready to make our call here. Pressure, temperature, and dew point are the things that we're going to want to get over the layer. We have heights, so we should go ahead and give it the heights. And then surface is fine. In this case, we can say something like depth equals 3 kilometers. Then we have to assign these to something on the return. I'm just going to go ahead and overwrite my pressure, temperature, and dew point for now. That's fine. So now if we look, we see that we have pressures that now only go up to 677 hectopascals because we're only looking from the surface to 3 kilometers. Now we can calculate CAPE in the same way. So mpcalc, in this case, I'm going to do surface-based again, and pressure, temperature, and dew point. You see now that they are less because we're only looking over that surface to 3 kilometer layer. So I hope that you found this useful. This is a really requested calculation and one that I know a lot of people have already found and been using even since it was in development and not actually out in the wild. If you found this useful, please don't forget to subscribe to the Unidata YouTube channel so that you get alerts when videos like this are posted, and thumbs up to this video if you found it helpful. You can follow MetPy on Twitter. We are at MetPy, and we post on the Unidata Facebook page. You'll also find links to our GitHub repository where you can file issues or create pull requests down in the description of the video. Thank you for watching, and we'll see you on the next MetPy Monday.